Hello everyone, I am Dr. VRAO. In this lecture, let us try to learn about work functions in the thermodynamics. There are two work functions in thermodynamics. Those are Gibbs free energy, Gibbs free energy, and the second one is Helmholtz work function. Helmholtz work function, right? These two are work functions in thermodynamics. Before we are going to learn about these work functions, why these work functions are introduced? Because in most of the chemical processes, neither energy nor entropy are constant. Therefore, there is a need to introduce these two work functions, right? Right. Then we know that energy is converted into work. I repeat, we know that energy is converted into work. The portion of energy which can be converted into work is called useful energy, right? The portion of energy which is useful to do some work or useful work is called available energy, and the portion of energy which cannot be converted into useful work is called unavailable energy. Therefore, we can assume total energy is equal to available energy plus unavailable energy. That is, total energy is sum of available energy and unavailable energy, right? That is total energy. We can write total energy is equal to, what is the term, isothermally available energy plus isothermally unavailable energy. Right? Therefore, total energy is equal to, or total energy is equal to sum of isothermally available energy and isothermally unavailable energy, right? From the previous classes, we came to know that unavailable energy, we came to know that entropy is a measure of unavailable energy, right? From the previous classes, we came to know that entropy is a measure of unavailable energy, right? Entropy, S, is a measure of unavailable energy. When entropy is multiplied with a temperature, factor temperature, then it also measure of unavailable energy. So, we can write isothermally unavailable energy. Instead of isothermally unavailable energy, we can write this term, that is T into S. That is because S is a entropy, entropy is a measure of unavailable energy, and if it is multiplied by temperature, it is also a measure of unavailable energy, right? And let us say isothermally available energy, let us say X, and total energy, let us say Q. Total energy is Q, let us say Q. then this equation takes the form total energy Q is equal to X minus Ts, okay, where Ts refers to the isothermally unavailable energy and X refers to the isothermally available energy and Q refers to the total energy, right. So, if you want to know the, if you want to calculate the isothermally available energy, then you interchange this equation, that is available energy X is equal to that is available energy X is equal to Q minus Ts, right, Q minus Ts. So, X is a X refers to the available energy, Q refers to the total energy. What is total energy? The amount of heat that we are supplying to the system is total energy, right, that is represented by Q, and TSE is a measure of unavailable energy, right. For example, if the energy that we are supplying to the system is at a constant volume, for example, the heat that we are supplying to the system is at a constant volume, then Q can replace with the internal energy, because heat absorbed at a constant volume is nothing but internal energy, right. Heat absorbed at a constant volume is nothing but internal energy. So, for example, if heat is absorbed at a constant volume, then Q is replaced by ERU. E represents the internal energy, E minus Ts. For example, if Q, that is that heat that we are supplying to the system, is absorbed at a constant pressure, then Q is replaced with the H, because heat absorbed at a constant pressure is nothing but enthalpy, right, enthalpy. So, we can replace the Q with the H minus Ts, right. So, if heat is absorbed at a constant volume, then Q is replaced by E, and if heat is absorbed at a constant pressure, then Q is replaced by enthalpy, H minus Ts, okay. Then when Q is replaced by E, that is heat absorbed at a constant volume, then X can replace with the Helmholtz work function. Okay, Helmholtz assigned the letter A for this X term because heat is absorbed at a constant volume. Okay, that is total energy, and total energy minus unavailable energy, that is equal to Helmholtz work function, that is available energy. And if it is H, if it is Q is replaced with or heat is absorbed at constant pressure and Q is replaced with the H, and in this case X is replaced by G, right. Therefore, the two work functions are mathematically defined as A is equal to E minus Ts. This is called Helmholtz work function, right. This is called Helmholtz work function. A is equal to E minus Ts, right. And another work function is G is equal to H minus Ts, right. These are the two work functions. Why these work functions are introduced? Because in most of the chemical process, neither energy nor entropy are constant. Therefore, it is not convenient to it is not convenient to define the spontaneity of the process. So, these two work functions are introduced. Okay. Now, let us know about the significance of Gibbs free energy, right. Significance of Gibbs free energy. Already we know that the Gibbs free energy, mathematically the Gibbs free energy is defined as G is equal to H minus Ts. G is equal to H minus Ts, right. Okay. And Gibbs free energy is nothing but isothermally available enthalpy. Okay. Another definition for Gibbs free energy is isothermally available enthalpy, right? G is equal to H minus Ts. Now let us know the significance of Gibbs free energy. Okay, we know that from first law of thermodynamics, we can write delta U is equal to Q minus W, and this is the equation for work done by the system. Of course, if it is work done on the system, then Q plus W, right? Okay, this is the equation for work done by the system, right? Work done by the system. Right? So, delta U is equal to Q minus W, right? But this is the work term, okay? But this work includes two types. This work includes two types. What are they? That work includes two types. That is expansion work, and another one is non-expansion work, right? Expansion work and non-expansion work. So this work, this work includes two types, that is expansion work and non-expansion work, right? So let us try to understand these two types of works by taking the example electrolysis of water, right? Electrolysis of water. So the chemical reaction that is that takes place in electrolysis of water is 2H2O gives rise to 2H2 plus O2, all right? 2H2O gives rise to 2H2 plus O2. Here in the electrolysis of water, there are two types of works. One work is expansion work and another work is non-expansion work. Okay, let us see about non-expansion work. Non-expansion work is also called as electrical work. Non-expansion work is also called as electrical work, right? And expansion work is also called as mechanical work, right? Mechanical work, right? Okay, in the electrolysis of water decomposes into H2 gas and oxygen gas. This is called non-expansion work. Right? Besides that, in the electrolysis of water, 2 moles of water or 2 moles of reactant decomposes to give 3 moles of products. That is, here the reactants are 2 moles, products are 3 moles, that is volume increases. Okay, so that includes expansion work, right? So non-expansion work non-expansion work that is water decomposition, but expansion work is increasing the volume. So expansion work is nothing but to increase the volume of this system, right? So we can write delta U is equal to Q minus this work includes expansion work, W expansion work minus W non-expansion work, right? Okay, so and Q is minus expansion work is nothing but mechanical work. Mechanical work in thermodynamics, work is always what is it called, mechanical work, and instead of mechanical work we can write that is always represented by P delta V, because that is associated with the change in volume. Okay, change in volume. So the expansion work is delta PV, P delta V or P delta V minus W non-expansion, right. So from this we can rearrange this equation, that is that is possible. Okay, right. From in next step, delta U plus P delta V plus W non-expansion is equal to Q, right. And delta U plus P delta V, we can write delta H, because H is equal to E plus PV, right, or U plus PV, right. So delta U is equal delta U plus P delta V. Instead of this term we can write delta H plus W non-expansion is equal to Q, right, Q. Next, from second law of thermodynamics, we know that delta S is equal to Q reversible by T. Therefore, T delta S is equal to Q reversible, right, or Q. So instead of Q we can write T delta S, that is delta H plus W non-expansion work is equal to T delta S. Okay. In the next step, we can rearrange this equation, that is delta H minus T delta S is equal to minus W non-expansion, and delta H minus T delta S, this can this term the delta H minus T delta S can be written as delta G, because G is equal to H minus Ts and delta G equal to delta H minus T delta S is equal to minus non-expansion work. Okay, non-expansion work is a useful work. Okay, non-expansion work is a useful work, because by that non-expansion work, that is electrical work. Here the electrical work is non-expansion work, and that non-expansion work did decomposition of water into hydrogen gas and oxygen gas. Actually that is useful work. So that non-expansion work we can write W useful work, and in the next step W useful is equal to minus delta G. Therefore change in decrease in free energy is a measure of useful work, right. Decrease in free energy. Okay, W useful work is equal to minus delta G. This means that, or this equation states that decrease in free energy is a measure of useful work. Okay, that means that with decreasing the Gibbs free energy, decreasing in Gibbs free energy is a measure of useful work. Greater the free energy of the system, higher is the useful work. Okay, so this is the significance of Gibbs free energy. I hope you learned something, and if you really learned something, please extend your support by like, share, comment. Thank you for watching.